Okay, so this is going to be a really quick run through of section 3.9, which is about something we call antiderivatives. This is some silly putty that I bought. Maybe next time I'll open that up and mess around with it. Antiderivative. So an antiderivative, this is just our definition. An antiderivative function f of x is called an antiderivative for the function little f if, when you take its derivative, you get little f back. Okay, so it's the definition of an antiderivative. So it's the opposite of a derivative. Okay, so this function here is the antiderivative of this function here, because when you take the derivative of this function, you get that function. Okay, so it's sort of like the reverse of taking the derivative, which is why it's called an antiderivative, of course. So let's just think about this for a minute. Just some examples. So we could consider an easy function like x squared. Let's try x squared here. So this function is the antiderivative of this function. Excuse me, 1/3 x to the third, because, I'm sorry, what am I doing? Is the antiderivative of this function here, 2x, sorry, I'm getting mixed up here. Why? Because the derivative of this function is equal to 2 times x. Okay, so that is the derivative of big F is equal to little f here. Okay. So that's just an example. Now let's consider derivatives and antiderivatives for just a minute. I want to draw the graph of a few functions here. Let's start off with just the graph of x squared. Okay. So this is the graph of x squared. Now I'm going to draw exactly the same graph but shifted up by, let's say, 1. So this is x squared plus 1. We all know that's just the graph of x squared just shifted up by 1. And we could draw another graph here, the graph of x squared minus 1, which is just x squared shifted downwards by minus 1. Now let's take the derivatives of each of these functions. Okay, if we take the derivative of x squared plus 1, then we get 2x, of course, because that's a constant, so it becomes 0 in the derivative, and x squared becomes 2x. The derivative of x squared is 2x, it's the same, and the derivative of x squared minus 1 is also 2x, so these are the same. Okay, so what does that mean? That means that x squared plus 1, x squared, and x squared minus 1 are all antiderivatives of the function 2x. Okay, this is very, very key. Okay, and what it illustrates is the following theorem, which says that, so theorem, it says if f, big F, is an antiderivative of little f, then so is f of x plus c, where this number here, c, is any constant. Okay, and if we go back to that example there, so our previous example, f of x is equal to x squared, then f of x plus c is just x squared plus any constant. And if we look at the graphs of these, then we have x squared, and we have shifted copies of x squared everywhere. Okay, these are what all of the different copies of x squared plus c, where c is allowed to be any number here. We could just take this graph and shift it upwards or downwards depending on what that constant is. And if we look, let's say right here, okay, then the slopes, let me use another color, then the slope right here, and the slope right here, and the slope right here, and the slope right here, those are all the same slopes. Okay, so that's exactly what's going on here in this derivative antiderivative process. If a function is an antiderivative of another function, so in this case, little f of x is 2x. If a function is an antiderivative of another function, then that means that at a point where it has its derivative equal to that function, any shifted copy of big F here will have the same slope at the corresponding x value there. So this is just a geometric illustration. So we call f of x plus c is the general antiderivative of little f of x in this case. The general antiderivative. So anytime you have one antiderivative of a function, then you can create the general antiderivative by writing that antiderivative plus this constant, which is allowed to just be arbitrary. All right, let's look at some examples. Find antiderivatives of these functions. Okay, one. Let's try sine of x. So here, little f of x is sine of x. Well, we all know a function whose derivative is sine of x. Sine and cosine are related by their derivatives, and so we might guess, so we're just guessing here, we don't have any techniques, that if we take f of x to be minus the cosine of x, then this will work, okay? F prime of x is equal to the derivative of minus cosine of x, which is minus times minus sine of x. And then the minus sine of x is the derivative of cosine. The negative here comes along for the ride because it's just a constant on the outside of this function. And then these two minus signs will cancel, and we get sine of x. So there, we've just verified that minus cosine of x is an antiderivative of sine of x. So the general antiderivative is minus cosine of x plus c. Okay, so there's one example. Let's try another example. So how about if we take x to be any power? Let's make this n bigger than or equal to 0. So examples of this would be x itself, x squared, x cubed, x to the 1/2, and so on. So n could be any positive number. So we guess. Well, let's see. We want something here that when we take its derivative, we get this. Okay, we can't quite do that. Okay, when we took the derivative of this, we would not get quite the right answer if you take a look at how that goes. So if we check, we would bring the n plus 1 down, and then we would subtract 1 from the power there. But that's not quite this. It differs by that. Okay, so we have to guess again. And we say, well, how about if we take this thing and just divide by that number to cancel out the multiplication that's going to happen a little bit later. So if we check this, we get the derivative of n plus 1, x to the n plus 1 over n plus 1 is, well, the n plus 1 will come down, and then we will subtract 1 from that power there, and we get n plus 1 down in the denominator. And of course, this is n plus 1 in the denominator and a copy of n plus 1 in the numerator, so they cancel, so we get x to the n. So, so it works out. So that means that x to the n plus 1 over n plus 1, another way to write this might be 1 over n plus 1 times x to the n plus 1, is the general plus c is the general antiderivative. Okay, so this is the general antiderivative, I guess plus c, is the general antiderivative of x to the n plus 1. What about a third example? How about x to the minus 3? So this is 1 over x cubed. This is our little f of x, okay? Same thing, right? The guess should be, well, we want to pick something where the power is increased by 1, and then divide by that power so that it will cancel when we take the derivative of this. So let's simplify this. We get minus 3 plus 1 is minus 2 over minus 2. Okay, maybe another way to write this would be minus 1 over 2x squared. Okay, something like that, but let's check. So we get the derivative of x to the minus 2 over minus 2. Take its derivative. We bring the minus 2 down. Okay. Subtract 1 from the power, so minus 2 minus 1 is minus 3. And then those minus 2's will cancel each other. So we get x to the minus 3. So perfect. That's exactly what we have up here. So the general antiderivative is, it's this, minus 1 over 2x squared plus any constant. So this is our antiderivative. Okay. So that's antiderivatives there. Let's take a look at a slightly more specific example. I want to find little f if we know that f prime of x, if we know its derivative, is equal to x times the square root of x, and if we know that when we plug 1 into the function, we get the number 2 out of here. Okay, we'll come back to this later. This is what we call an initial condition. An initial condition on the function f of x. Okay, let's first find the antiderivative of this function. So f prime of x is equal to x times the square root of x, which is equal to x to the 3/2 power. Okay, right? This is 1 copy of x, and this is half a copy of x, so we add 1 and a half, and we get 3/2. So this is what f prime is. If you want to find out what f is, well, we use the rule we just learned on the previous page. You add 1 to this power, and then you divide by the new power here. And then, of course, we want the general antiderivative, so we're going to do plus c here. And, well, let's write this out. So this is x to the 5/2. 3/2 plus 1 is 5/2. And then down here we have 5/2 plus c. And if we simplify this, which I would like you to simplify this a little bit, we get 2/5 times x to the 5/2 plus c. Okay, very good. So this is our general antiderivative, right? This is just general. But we want something more specific. We want a function where when we plug in 1, we get 2. So let's see what that is. So f of 1 is equal to 2/5 times 1 to the 5/2 power plus c. So 1 to any power is just itself, so 2/5 plus c here. Okay, but we want this to equal to 2. So we need this, we want this to be true. Okay? And so in order to do that, we have to figure out what c is. Well, c is obviously just 2 minus 2/5. So c is equal to 2 minus 2/5. What is that? That's 1 3/5, or I guess 8/5. So that means that the final answer for this is take that value of c and put it there. So we get 2/5 x to the 5/2 plus 8/5. This is our answer. So you will notice, if you take the derivative of this, then you'll bring the power down. So that would be 5/2 times 2/5, so it will cancel. And then you'll subtract 1 from that, so you will get x to the 3/2. And then this is a constant, it will go away, so that will be it. So this is indeed x to the square root of x, or x times the square root of x. And we notice that when we plug in 1, we get 2/5 plus 8/5, which is equal to 2, okay? So this was the task. Find a function whose derivative was that, and who, when we plug 1 into that function, we get 2. Okay, so this is the function that does it. Okay, this is finding a specific antiderivative. This isn't the general antiderivative anymore. This is a specific example of a derivative. All right, let's try to do this with another example. Find f of x if the second derivative of f with respect to x is equal to 12x squared plus 6x minus 4, and we want f of 0 to, f of 0 to equal 4, and f of 1 to equal 1. Okay. So remember, in the previous example, we had one derivative and one initial condition. Here, because we're taking the second derivative, we're going to require two initial conditions to really fully answer this question. Okay, so let's do this. First, find the first derivative. Okay, so we know that f double prime is equal to 12x squared plus 6x minus 4. So that means that we can take a guess at what this first antiderivative is, right? So going from 2 primes to 1 prime is just going backwards by taking antiderivative once. So let's use our rules. We want to raise the power x by 1 and then divide by the new power. Okay, that takes care of that piece. This piece here, we want to raise the power by 1, divide by the new power, and then here we raise the power by 1, so there's no power here, so raising it by 1 is, I'm just going to put an x in there, and then we get a constant in here, okay? So that's the first derivative, all right? We don't know what this is yet, but we'll find out, okay? Now, find f. Find f. And we're going to use this information, okay? So f is equal to, let's see, so if we raise this power by 1, we get 12x to the 4th. Divide by the 4, so 3 times 4 will be 12. And then plus, okay, we're going to raise this power by 1. And then divide by the new power, so 2 times 3 will be 6. And then we're going to raise this power by 1. Divide by the new power, okay? And now this is the tricky part, not too tricky, but it's a tricky part anyway. This was a constant, so it's going to pick up a copy of x, okay? There was no copy of x there before, it was just a number. Now we pick up a constant, and then we have another constant, something that would go to 0 if we took the derivative of this. So this is our most general antiderivative. So f of x equals, let's simplify this a little bit, it's silly looking here. X cubed minus 2x squared plus cx plus d. Okay, so this is the general antiderivative right here. Now we're going to use the initial conditions. Okay, now we use the initial conditions. We know that when we plug in 0, we should get 4. So we get 0 plus 0 plus minus 0, that'll be 0, so we get d here when we plug in 0, and this has to equal 4. So that means d equals 4. Okay. Same thing as before for 1. We plug in 1, we get 1 plus 1 minus 2, so those will all go away, plus c, and then plus d, which is, but we know that d is equal to 4. So we get 4, and this whole thing has to equal to 1. Okay, so that means that c is equal to minus 3. Okay, now with all of that, we can write down our final answer: x to the 4th plus x cubed minus 2x squared, and then we have a minus. Wrote a plus there, but it's a minus. C minus c times x, so that's a 3x, and then d is equal to 4. So this is our answer. Okay, so this is a function that when you take its double derivative, you get 12x squared plus 6x minus 4. And if you were to plug in 0, you get 4. And if you were to plug in 1, you'll get 1. Okay, so this is the answer. This will be how these always go when you have a derivative or a second derivative and some initial conditions here. All right, let's see a specific example of this particle motion. Okay, so a particle moves in a line with acceleration, let's call it a of t, how about 6t plus 4, okay, and initial velocity so initial velocity means at time 0. Its initial velocity, let's say, is minus 6 centimeters per second. And initial displacement, let's say initial position, so that is the position at time 0, let's say 9 centimeters. Okay, so find the formula for, let's say, v of t and s of t. So this is what we want to find. Now remember how s of t and v of t are related. So the velocity of a particle is equal to the first derivative of its position, and the acceleration of the particle is equal to its derivative of its velocity, which is the second derivative of its position. All right? So now if you think very carefully about this, this is actually exactly like the previous example where this was f double prime, and we had two conditions on previous antiderivatives of the thing. So we're going to find this. So the solution to this is, well, find v first. Okay, so we know that the acceleration is 6t plus 4. So that means if we look at the antiderivative, right, v prime is equal to a, so to find v from a, we take the antiderivative. We use our rules for finding antiderivatives here. We raise the power by 1 there, divide by the new power. We add this, we raise the power of t that we see there, which is t to the 0, so it becomes t to the 1. And then we have a constant c here. So that means v of t is equal to 3t squared plus 4t plus c. Okay? But we know that when we plug in 0, we get 0 plus c, and this has to equal minus 6, right? So that's our initial condition on the velocity when t is equal to 0. So v of t is equal to 3t squared plus 4t minus 6, okay? Now, we use this to find s. Okay, anti-differentiate, right? V is equal to the derivative of s, so we So we undo this. I'm going to skip the dividing part, right? You raise the power by 1, which will be t cubed, and then you divide by 3, so it will cancel that 3. And then here, we raise the power by 1, so t becomes t squared. Divide by the new power is 2, so 4 divided by 2 is 2. And then we have minus 6 times t, no t there, so a t pops up. And then we have another constant here that could vanish when we take its derivative to get the velocity, right? So this is our general form of the antiderivative of s, but we know that when we plug in 0, we get 0 plus 0 minus 0 plus d, and we know that this is supposed to be 9. So therefore, s of t is equal to t cubed plus 2t squared minus 6t plus 9. And this is our this is the solution to this. All right, that's all that we're going to do in this chapter on antiderivatives. We'll discuss these problems in class.